I'm recording this paper for CADEWare 2020 conference. The paper is written by myself and a colleague from Sian Jiaotong Liverpool University, Thomas Fischer. And our paper is on the question of whether architectural design optimization requires multiple objectives. And we ask this question because something one can read quite often in the literature around optimization architecture is the idea that architecture design is about completing trade-offs and requires decision-making. And multi-objective optimization is also about trade-offs. It also requires decision-making. And so that one can then ask the question whether this means that multi-objective optimization is especially appropriate for architectural design optimization. And this is an idea that is implied or sometimes also explicit in the literature. In the paper, we discuss and also challenge 8 assumptions that would support this idea that multi-objective optimization is especially appropriate. You should these assumptions that we discuss and the challenges. Some of these assumptions are quite explicit in the literature, others are more implicit, and others are perhaps a bit overstated for the sake of discussion. So it's meant not so much as like a critique, saying one thing is better than the other thing, or saying that other people are wrong, but it's more an invitation to discussion, and the intention is to sharpen the discourse around optimization in architectural design. So the first assumption is that architectural problems are multi-objective problems. Well, this makes sense on a literal level that, of course, as architects, we always have multiple goals in mind, right? So they're rarely designed with a single aim, as one author says, or architectural design is concerned with bringing things together. But of course, in architectural design, we have many objectives, and often we cannot even elaborate all of the objectives at the beginning of the design process. And so this is already where this analogy with multi-objective optimization breaks down, because in multi-objective optimization we need to, of course, enumerate all of the objectives quantitatively, and in fact, from a practical standpoint, we cannot have too many objectives, because the difficulty of multi-objective optimization increases exponentially in the number of objectives. So in a practical sense, in my experience and from my reading of the literature, I would recommend to not optimize, try and optimize more than maybe 2 or 3 objectives. And therefore, optimization is a tool for rather than analogous to architecture design. And the second idea is architecture design optimization is limited to negotiating trade-offs. I would say if stated like this, clearly it's not true, right? Optimization is about many things. One of the things it is about is understanding trade-offs, but it's also about maybe having a starting point for further design steps. It can be about understanding relationships between design parameters and performance. And so it's too simple to think that the only thing that designers use optimization for is to negotiate trade-offs, and therefore this is not right. So therefore there might also be legitimate uses of single objective optimization in architecture design. Multiple objectives require multi-objective optimization. This is the next stage where you say, well, yes, designers often have multiple objectives, but that doesn't necessarily mean they need to use multi-objective optimization algorithms. They could also use a scalarization method like weighted sums, products, penalty functions, feasibility constraints to combine several objectives. And the only difference with multi-objective optimization is that in multi-objective optimization, you need to define your preferences about these different objectives after the optimization, while if you want to use single objective optimization with scalarization, you need to define your preferences before optimization. And so one can argue how important that really is, and sometimes I think it is very well possible to define these preferences before, the optimization begins. For example, a structure design, you could say it should be as light as possible and as safe as possible, but you could just as well say it should be as light as possible while meeting a safety constraint. And building on that, I think it is quite plausible to say architectural design is about negotiating constraints. And it's just as plausible, this framing is just as plausible as saying it's about negotiating many problems that have many objectives, right? And so, but then this different framing might suggest the use of different optimization methods. Number 4, Pareto fronts represent design spaces. Visually, you can already see there's two very different representations here. And the key point is that a Pareto front only visualizes relationships between objectives, while other types of representations, like the one on the right, visualizes also relationships between design parameters and objectives. And so the point is that Pareto fronts is not the only visualization of optimization results that might be relevant for designers. But this is sometimes something that people suggest. All right, so I have some quotes here where people say that, well, if you use scalarization, you do not have the context of the whole range of solutions, or if you don't use multi-objective optimization, you never see the whole picture. But this seems to suggest that if you use multi-objective optimization, you will always see the full picture and you will always see the whole range of solutions, and that's clearly not true, right? And so yes, Pareto fronts are a relevant visualization, but there are other visualizations, and it's not the be-all and end-all. Number 5, Pareto front graphs require multi-objective optimization. So now if I want to find a Pareto front, do I have to use a multi-objective algorithm? No, not necessarily. In this picture, I have used mostly single objective algorithms and one multi-objective algorithm. And in fact, the best front, which is the dotted line, is generated by combining the results from one single objective algorithm and from one multi-objective algorithm, and from which we can see just by example that multi-objective algorithms are not necessary and not sufficient to derive Pareto front graphs. Number 6, multi-objective algorithms are efficient and robust. That is something one can read quite often. Here are some results from a paper I will be presenting at EKD with Francesco De Luca. And you can just see here, there's several different multi-objective algorithms that have different performance. Some perform quite well, others perform not so well. And especially the NSGA2 algorithm, an evolutionary algorithm that is very popular as a multi-objective algorithm, is the big blue box. The light blue box on the right has the largest variability in these results. So the evolutionary multi-objective algorithm in this example is the least robust algorithm. And also in general, compared with single objective optimization, much less is known about multi-objective optimization. So there's less mathematical proofs and there's less benchmark results. And therefore, we should be careful to generalize about the performance of multi-objective algorithms. And we should not necessarily trust that just one single run of one algorithm on the very difficult problems with many objectives will give something. It will yield an accurate Pareto front. In fact, it's likely, I think, that many Pareto fronts in the literature in our computational design field are not accurate, and further testing would reveal better Pareto fronts. Then building onto that, one could think that, oh, maybe it is evolution that makes multi-objective algorithms efficient and robust. Again, this is an assumption one can see in the literature. But evolutionary algorithms don't necessarily have a lot to do with evolution, with biological evolution as we understand it today. And so this analogy just fails because since the development of the first genetic algorithms, the insights in biological evolution have advanced. And so number one, evolutionary algorithms have not a lot to do with evolution. And number two, even if they had a lot to do with evolution, that still doesn't necessarily mean that they would work very well, right? This is kind of a naturalistic fallacy to think that. And we would need more empirical evidence to actually be sure that this is correct, but I've already shown you some empirical example where this is not true. Then finally, there's sometimes one can read an idea that computational cost is negligible because multi-objective optimization is more difficult. Therefore, there's a higher cost associated with it, which is an argument against it. And then we have to balance this cost against the insights we can get from the Pareto front. But in terms of and then one argument would be to say, well, but the speed of computers is always increasing, but it's not true anymore, right? Moore's law is dead. So as you know from your personal experience, the speed of the clock speed of a single CPU is actually not really increasing anymore these days. Instead, we have parallel computing, cloud computing, but these technologies are useful for optimization only in a limited sense because they enhance the exploration step, where we try to understand the fitness landscape as a whole, but they do not enhance the exploitation step, where we want to zoom in and refine the very best solutions. And so there's diminishing returns in that. And therefore, this difference in difficulty matters between multi-objective and single optimization. And also this calls into question this idea that the insights that we get are so valuable that we should accept the cost. Because what this really implies is where if the cost is very high, so if the problems are very difficult and we need many steps, it's likely we're not going to get accurate results. And therefore, we cannot really trust the results. And therefore, the value of our insights also decreases. So to wrap up, optimization is a tool for rather than analogous to architectural design. And this tool is not only about trade-offs. We can use scalarization if we want more accurate optimization results by simplifying the problem and using more efficient, more grounded single objective optimization algorithms. Pareto front graphs are not a replacement for other representations of design spaces. One can also generate Pareto front graphs with single objective optimization and scalarization. Multi-objective optimization is exponentially more difficult than single objective optimization, and on the other hand, lacks efficient algorithms in the sense that algorithms that reliably yield an accurate Pareto front in, let's say, hundreds of steps. I don't think we really have that, but this is something we would need once we do more costly simulations like energy simulations, daylight simulations, CP simulations. And I think that's quite clear. Evolutionary multi-objective algorithms are not analogous to biological evolution. And finally, the high computational cost of multi-objective optimization remains a problem. And this leads to some practical recommendations to only use multi-objective optimization when one wants to understand trade-offs. Otherwise, one should use scalarization. One should only use multi-objective optimization when one can run many optimization steps, ideally thousands or even tens of thousands. When using multi-objective optimization, one should try to reduce the objectives, again, to reduce the difficulty and the computational cost. And one should always be aware of this alternative, which is using scalarization and single objective algorithms. Which then means for research that, of course, an important direction would be, or is, in fact, to develop more efficient algorithms for simulation-based multi-objective optimization. So on the one hand, I think this can mean enhancing the effectiveness in terms of solving optimization problems with a small number of objectives. There's also another field of looking into how to enhance the effectiveness of solving problems with many objectives. But again, many objectives automatically also means many, many more optimization steps. Another research direction would be to make scalarization easier and more intuitive. And finally, one should also look more closely at how designers actually use optimization from an empirical point of view. so with user studies and surveys, because a number of the arguments we discussed in the paper are conceptual arguments, like there's analogy between architectural design and the nature of multi-objective optimization algorithms, or the analogy between biological evolution and evolutionary algorithms. But as I said, so these are sort of conceptual arguments, and I think it's important to supplement these conceptual arguments with empirical evidence. Thank you very much.